The next thing we're going to take a look at is NumPy, which is one of the many powerful and widely used data manipulation and analysis modules available for Python. NumPy provides the ndarray data type, which gives you very efficient and flexible n-dimensional arrays with highly efficient vectorized math functions, linear algebra capabilities, random number generators, and the like. Some of the other important and widely used modules that we'll take a look at in Financial Computing 1 include pandas for things like time series and spreadsheets, SciPy, Statsmodels, which gives you a variety of statistical models, probability distributions, and the like. And we'll also see modules for plotting data, for scraping data from websites, and so on. Most widely used modules have a sort of standardized naming convention for module abbreviations. For example, the NumPy module is usually imported as NP, pandas is imported as PD, and so forth. For now, we're only going to worry about NumPy. And let's start taking a look at the NumPy ndarray data type. So we're going to import NumPy as NP, and we're going to compare and contrast NumPy's ndarray data type with the built-in list data type in Python. We know that we can create a list of a sequence of integers using the range function with the list constructor. Here, ls1 contains 0 through 4. The equivalent thing for NumPy is called an arange, the NumPy array-based equivalent of the range function. So np.arange builds a NumPy array whose data type is ndarray, which similarly contains the values 0 through 4. An important difference here is that items in an ndarray are guaranteed to be stored in contiguous memory locations, and access to the elements in an ndarray is much more efficient than access to the elements in a Python list. This efficient access comes with a price. An ndarray is not able to store arbitrary precision Python int values. Instead, an ndarray stores a more restrictive range of integer values, similar to the int values found in the C and C++ languages. Okay, so here we see that the type of ls1 is list, and the type of ls1 sub 0 is int. Let's confirm that. So the type of ls1 is list, and the type of ls1 sub 0 is going to be Python int, whereas the type of a1 is the NumPy module's ndarray data type, and the type of a1 sub 0 is something called an int32. So that means that it's a 32-bit wide integer value, and it turns out that the range of values you can store in an int32 is a little bit beyond plus and minus 2 billion. Not nearly the arbitrary precision range that we have with Python ints. An ndarray is iterable, so you can step through it using for loops. It's also very easy to convert back and forth between ndarrays and the various Python collection types. Okay, so here's my ndarray a1, and I can say for I in a1 do something. Just print I, let's say. I can easily create a list from a1, or a tuple from a1, or a set from from A1, and so on. Okay, so V is a list, T is a tuple, S is a set, created from the items in A1. Not only can you use an ndarray to create these various built-in collection types, but you can go the other direction as well. You can use the various built-in collection types to create ndarrays. And here, rather than arange, you use the function array. So I'm saying A2 gets np.array, and then I can give any iterable that I wish. For example, here's a list, 3, 4, 5, 6. And whoops. And here is my A2 array. In this next example, I have a tuple of floats. I'm going to cheat and abbreviate. Okay, so here is my tuple contained between these parentheses, and now I'm going to create an ndarray of floating point values. Now, these are not Python floats. What they are, let me look at the type of the very first item in this array of 2 items. Okay, so A3 is an ndarray of 2 floating point items. Whoops, I accidentally looked at A2 sub 0. Let me look at the type of A3 sub 0. And what we see here is that this is a float 64 rather than a Python float. Now, it happens, actually, that a Python float is the same shape and the same pattern of bits as the NumPy float 64. So the range and magnitude of values that you can have in a Python float are identical to those that you can have in a float 64. In C or C++, there's a data type called double that would be the equivalent of the 64-bit floating point type. Now, we know that a list or a tuple or a set can have items of different data types. I can create a list containing an int and a float and a bool, and this is no problem. But it turns out that an ndarray, because of how it's implemented and because of the desire for efficiency, all of the items in an ndarray have to be the same data type. And so if you attempt to create an ndarray using mixed data types, here I have a list containing an int, and let me be clear, this is a Python int, a Python float, a Python int, and another Python float. NumPy is going to do something called upcasting to convert all of these values to the same data type, which in this case is going to be the float 64 data type within the NumPy module. All right, so here I'm saying A4 gets np.array, and then I have my list, Python int 3, Python float 4.5, Python int 5, Python float 6.7. But these are all going to get upcast to float 64 and therefore displayed as 3 point rather than integer 3 and 5 point rather than integer 5. I can check the type of one of these to make sure. A4 sub 2, let's say. All right, A4 sub 0, sub 1, sub 2, that's this guy, and its data type is, whoops, its data type is float 64. Sometimes this upcasting can result in surprises. For example, here I'm creating an ndarray from a tuple containing a float and a string, a str. Now, NumPy decides here that a string is a more complicated data type than a float, so it converts the float to a string so that everything in this array is represented as a string. So we have a string 3.14159 rather than the floating point value 3.14159. When I ask to see A5 here, not only do I see the values within the array, but the data type of these values is also reported to me. And this encoding here, the less than symbol U32, means that the items in this array are stored as Unicode 32-bit characters, character sequences. If I create an ndarray using a very wide mixture of types, here I have a Boolean, the special value none, and an int. Here, NumPy just sort of gives up and says, well, okay, fine. All of these are objects, and I'll just keep track of each one of them independently as some kind of object. And if I look at the types of the individual values in this array, I get told which type of object each one of these values is. We know that if we have a list object like ls1, that the star operator means to do repetition. So ls1 times gets 2 is going to give me 2 copies of ls1 appended together into a single list. If I say ls1 plus gets a single value, like 1, that's actually an error. Plus here means concatenation, but the thing on the right side of the plus gets operator has to be an iterable, not an individual int object. Right, so if I say ls1 plus ls1, let's say, this will give me the concatenation of 2 copies of ls1. For ndarrays, the star and the plus are treated mathematically rather than as concatenation and repetition. All right, so I have my array A1 containing these 4 int32 values. If I say A1 times gets 2, rather than getting 2 copies of that concatenated together, what I get is all of the items in A1 multiplied by 2. All right, so it started out containing 0, 1, 2, 3, 4, and now it contains 0, 2, 4, 6, 8. I can say A1 plus gets a scalar, and that has the effect of adding the scalar to each of the items within the array. So instead of 0, 2, 4, 6, 8, I now have 1, 3, 5, 7, 9. And if I add A1 plus A1, this gives me a vector sum rather than a concatenation. So the value of that thing is an ndarray containing 2, 6, 10, 14, 18. Okay, so star and plus and slash and minus are all treated as mathematical operators for ndarrays rather than star and plus being treated as repetition and concatenation. Now, an ndarray is a sequence. We can ask for a slice of an ndarray. That slice is always going to be a view on some underlying part of the ndarray. And let me show you some examples to describe what I mean by this. We're going to create A2 as an A range from 0 to 9. All right, and if I ask for A2 sub 2:6, that means from sub 2 up through but not including sub 6. So that slice is going to be these values here, 2, 3, 4, 5. But it is not merely a shallow copy of those values as it would be for a list. It is an actual view, like a window on those 4 values. And consequently, if I say A2 sub 2:6 gets a scalar, minus 8 in this case, what will happen here is that each one of those values 2, 3, 4, 5 within A2 itself are going to be replaced with -8. Okay, so I have modified A2 by assigning -8 to each of the int32 values in that view. Similarly, if I were to say A3 gets A2 sub :3, all right, :3 means all the values up to but not including sub 3, so sub 0, sub 1, sub 2. But here again, this is not a shallow copy. A3 is a view on the first 3 items within A2. And so if I say A3 times gets 3, that's going to multiply each of those first 3 items by 3, and I'll see that reflected back in A2 itself. All right, so instead of 0, 1, -8, I now have 0, 3, -24 as the first 3 item values within A2. To get a copy, you must use the .copy method. So here I'm saying A4 gets A2 sub :5 .copy. All right, so :5 means 0 through and including 4, so I'll get these first 5 items from A2. But this time I will get a shallow copy of those, not a view on those. So here's A4. And if I say A4 times gets -1, that only changes A4. It does not change A2. Okay? So A4 is, because of the .copy method, an independent copy of part of A2. Okay, so far we have looked at one-dimensional ndarrays. Now we would like to take a look at more general n-dimensional ndarrays. One straightforward way of creating an n-dimensional array is to use the array construction function with a list of lists for a 2-dimensional array, or a list of lists for a 3-dimensional array. Similarly, you could use a tuple of tuples, or a tuple of tuples, and so forth. Here on slide 33, I'm creating a variable A1, which is going to refer to a 2-dimensional ndarray. And I'm initializing that using a list of lists. So my first list is 1, 2, 3, 4. My second list is 6, 4, 2, 0. I've got a list of lists, and when I then display A1, the ndarray is displayed as this 2-dimensional array. I can use the ndim attribute of an ndarray to find out how many dimensions the array has. Here, as I claimed, we have a 2-dimensional array. And I can also find out the full shape of the ndarray by using the .shape attribute. Notice that ndim and shape are attributes, not methods that you have to call with parentheses. So we can see that A1's current shape is 2 by 4. That is, you can think of it as 2 rows and 4 columns. Another way of creating an n-dimensional array is to start out with a 1-dimensional array of some kind and reshape the ndarray. So here I'm using arange to create a 1-dimensional array of 0 through 11. A2 is my variable referring to that 1-dimensional ndarray. And we can see that the number of dimensions of A2 is 1, and the shape of A2 is 12. Now the shape is always reported as a tuple. All right, so for A1 up here we got a tuple, 2 comma 4, indicating 2 rows, 4 columns. Here we're getting a 1 tuple because we only have 1 dimension, indicating that this ndarray A2 contains 12 items. Reshape allows me to make a copy of some existing ndarray in which the copy will have a different shape. Here I'm specifying 3 as the number of rows, 4 as the number of columns, and because A2 does contain 12 values, this reshaping will work. A3 now is a 3-row, 4-column copy of A2. A2 itself is not changed. A2 itself is still one-dimensional. Certain special shapes and kinds of arrays can be created directly with some construction functions shown here on slide 35. For example, np.ones, if I create this as a 3x5 array, notice that my shape here is a tuple. So this is going to give me 3 rows and 5 columns of ones. Likewise, zeros behaves the same way, except for giving me zeros instead. All right, so here I have 2 rows and 5 columns of zeros. If I want an array, all of whose values are the same value, then I can use np.full. And I specify my shape, 5x5 in this case, and then my value, 3.14, let's say. And now I have a 5x5 array of the value 3.14. Either EYE, or identity can be used to create an identity matrix. So if I say np.I10, I have a 10 by 10 identity matrix, or np.identity, let's say 8, gives me an 8 by 8 identity matrix. So if you need an identity matrix of a certain size, you can use either one of those two functions equivalently. Now, you might have an ndarray that is quite large. For example, you might have 10 years worth of closing prices for a couple of thousand stocks. Roughly speaking, there are 250 trading days in each year. So if we have 10 years, that's going to be 2,500 days. We might have a row for each day, and then we might have a column of each stock. So this would be a 2,500 by 2,000 two-dimensional array of stock closing prices. It would be very common in a case like this to want to select only certain stocks and or only certain years out of this large data set, and we can use slices to do this kind of thing. So let's take a look at how we can use slices in two-dimensional ndarrays. First, let's see how to access an individual cell within a two-dimensional ndarray. We have this array A3, which has 3 rows and 4 columns. If this were a list of lists, we would be able to say something like A3 sub 1, let's say, to access the sub 1, that is the second row within this object, and in fact we can do that here. And then we can say A3 sub 1 sub 2, let's say, to access the sub 2 item within the one-dimensional array A3 sub 1, and that gives us the 6. But with an ndarray, we can go ahead and just use row, comma, column notation as we would in regular mathematics to access a particular cell within a matrix. So I can say A3 sub 1 comma 2 as a more familiar way of accessing this item 6 in row sub 1, column sub 2. A3 sub 0 comma 0 is the upper left value. A3 sub 2 comma 3 is the lower right value, the 11. Now let me create this 3x5 array that we're calling A1 shown here on slide 36. I'll go ahead and just hammer this in. Okay, so here's my list of 3 lists of 5 items from which I'm going to create the ndarray A1. A1 A1 is a two-dimensional. Whoops, sorry. A1 is a two-dimensional ndarray, and its shape is 3 by 5. Now let's suppose that I wanted to access just part of this two-dimensional array. For example, if I wanted to access these 6 items, the lower left part of A1, I can do that by saying A1 square bracket and then 1 colon, meaning as a slice that I want all of the rows in A1 starting from row sub 1 to the end. Okay, since there's only 3 rows in A1, this is going to give me row sub 1 and row sub 2. Then for the columns, if I say colon 3, that means columns sub 0, sub 1, and sub 2. Okay, so for rows sub 1 and sub 2, and for columns sub 0, sub 1, and sub 2, give me a view on just that part of A1. This is a view, so if I were then to say something like A sub 1 colon comma colon 3 times gets a minus 3, then all 6 of these items in the lower left part of A1 will have their values multiplied by minus 3. And the top row of A1 and the 4th and 5th columns of A1 are unaffected. Okay, so we've used slice notation to indicate which range of rows we want, and within those rows, which range of columns we want. Okay, so A1 is our 3-row, 5-column ndarray. A1 sub 2 is the row sub 2, that is the last row in the array A1. That is itself an ndarray, so I can ask for the shape of that ndarray, and I'm told this is a one-dimensional ndarray with 5 items, and in fact the number of dimensions is just 1. Okay, so if I say A1 sub 2 sub 1 gets 5, that basically means the same thing as saying A1 sub 2 comma 1 gets a 5, and we're going to end up putting a 5 right there. A sub 2 is the last row. A sub 2 sub 1 is the second item within that last row, and that's going to be changed to 5, as we see here. All right, now in slide 38, we're asking for a single row and all columns by using the slice notation. Recall that colon all by itself means from 0 up to but not including the length of the columns. So A1 sub 2 comma colon is really the same thing as A1 sub 2. It gives me all of the columns of that row sub 2. The shape of that indicates that there are 5 items in that row, and the number of dimensions of that row is just 1. It's a vector, it's not a two-dimensional matrix. But if I change the row 2 to the range of rows starting from row 2, so that now I'm asking for a slice of rows, even though row 2 is the last row in that array, my result is going to be a two-dimensional ndarray. Rather than being a one-dimensional ndarray containing 5 items, this is going to be a 1 by 5 two-dimensional array, as we can see by taking a look at the shape and the number of dimensions. asking for A1 sub 2 colon is equivalent to asking for A1 sub 2 colon comma colon, that is all of the columns from all of the rows starting from row sub 2. Now, here on slide 40, we're specifying that we want all of the rows, but only some of the columns. So A1 sub colon means that we want to get a view on all of the rows, and then colon 2 means we only want to get the columns sub 0 and sub 1. This again is a two-dimensional ndarray with 3 rows and 2 columns, and ndim is 2. It's very important to keep track of the shape and dimensions of an ndarray, even when the ndarray only contains a single value. For example, here, again we have our array A, and if we ask for A1 sub 1 comma 2, A1 sub 1 is the second row, A1 sub 1 sub 2 comma 2 is going to be this minus 15. Now, that's a scalar, that's not an array, so that's a scalar value with no dimension. But if I ask for this range of rows from row 1 up to but not including row 2, even though there's only one row in that range, I get a slice rather than a row. And so when I ask for that slice and sub 2, I end up getting a one-dimensional array consisting of just the value minus 15. The same thing is true if I ask for row sub 1 and then columns sub 2 up to but not including sub 3. There again, I have a one-dimensional array containing the value minus 15. And then finally, if I ask for slices both in the row direction and in the column direction, but my resulting slice only has a single value in it, this is nevertheless a two-dimensional array. It's a 1-by-1 two-dimensional array. Okay, so I'm asking for A1 sub 1 colon 2, so row 1 up to but not including row 2. Then I'm asking for column 2 up to but not including column 3, so I'm getting just the single value 15, but treated as the single value within a 1-by-1 two-dimensional array. Okay, so this may seem a little bit picky and silly to be getting minus 15 as a scalar, minus 15 as a one-dimensional array in two different directions, row-wise and column-wise, and then minus 15 as a two-dimensional 1-by-1 array. But it is vitally important for you always to keep track of the dimensions of things and the types of things in order to know what attributes and what methods you can invoke on your objects. Failing to keep track of types and dimensions will result in getting lots of complaints about syntax errors from your Python environment.